everyone. Can I have your attention? Hello. Hi. You guys have an announcement today? He approved it? Yes.
Oh, fine. Thanks, Shane.
Hi.
That's better.
Thank you. I like it. So anyway, sorry I haven't been here in a little while. I was interviewing in States and just got back yesterday. But anyway, hi. Good to see you all again. Here's the SI schedule. It's actually confirmed. So this is what we will be doing for the rest of the semester, the rest of the year, I guess. So if you guys have any questions or those times really suck, only if they really, really suck, send us an email. And I think that's about it. Jess, as you can see, she has a session tonight. She'll talk to you about it now. And then we have some other announcements, okay?
Hi. You should probably watch Blackboard for a worksheet for tonight's session. Hopefully there will be one before the session starts. We will cover everything that we have covered to date, probably in bits and pieces, but be prepared to, 1, participate, and 2, hear a really funny chemistry joke.
I lied, I'm not done. Sorry, I'm not done. One other thing. If you don't know where Bingham 103 is, it's on the quad. If you go out to the main quad, okay, you're coming out of Rockefeller and make a left, you'll run smack into the front of it, okay? And it's on the first floor. So Bingham 103, if you can't find it, email me. There's also maps online of campus. So Bingham 103. And the other thing is Wednesday, we're trying something new this semester. All of us will be there every Wednesday, okay? So it'll be kind of like a mini exam review. We'll go over everything up to that point. So it'll be comprehensive every Wednesday, and all 3 of us will be there to answer questions and to go over all the information, okay?
Hi, my name is Brian Jones. I'm the president of Alpha Chi Sigma, which is a co-ed professional chemistry fraternity here at CASE. We're going to be starting our recruitment rush events these next 2 weeks. So just kind of wanted to give you guys a little introduction as to what we are. We're one of the oldest chapters of Alpha Chi Sigma, which is a nationwide professional co-ed fraternity. And we do service events and just fun events around during the semester. We mostly run the Science Olympiad here that's hosted every winter at CASE. We work with local Girl Scout and Boy Scout troops to help them get their chemistry merit badges, and have recently been talking to Professor Kenney about starting to work with the local area high schools as far as doing tutoring and lab demonstrations.
All right, my name is Zach Wright, and I'm the vice president. We have lots of free stuff coming up over the next 2 weeks. Starting Wednesday in the atrium at 11:20 to 11:30, there'll be free Dunkin' Donuts, so delicious breakfast. Thursday, we're going to have a little thing in Twing. It looks like the 1914 room at 7:30 p.m. Come hang out, possibly food, movie, just kind of get to know people. Ice skating on Saturday, which is always fun, especially when no one knows how to ice skate. Sunday before the Super Bowl, we're going to try and get together a little football game. We'll go bowling on Tuesday, February 5th, free coffee that following Thursday, and then free Chipotle. And our final event is a wine and cheese event in the atrium, so come take advantage of us, get to know us, lots of free stuff. And also get to know your SI for this class. She's in the know. She'll help you out. So we look forward to seeing you guys.
Zach, I need one of those. Know the schedule there. And by the way, folks, I am a recent initiate into this fraternity. So I was initiated last fall. So I will be at one or more of these events as well. And 11:30 for breakfast, Zach, we need to work on that.
That's what time college students get up, I guess.
It's a good thing I don't teach at 9:30 like Butler. All right, thank you, gentlemen. And Jessica? Leave some calendars. Yep, you can leave them up front here. You pass them around, they'll be distracting me all hour. Don't do it.
All right.
They'll come get them up front.
We'll leave them up here.
I get distracted enough as it is. Thank you, sir.
Thank you very much.
Gentlemen, I'll see you later. We're still waiting for the thermite reaction. I don't see him. I will go up and talk with my demonstration and help assistant, and we'll get that to work.
You promised at the beginning of the year.
I did. I'll do thermite at some point. All right. Finishing up on physical properties of solutions. First of all, before I forget, Kappa will be coming, folks. I know you're all excited. I just emailed them this morning, so hopefully things will get up and running Wednesday this week. So, the question that just got asked is, am I going to put some sample problems up? Actually, since I left here Friday afternoon, I don't even remember what time I woke up. Yes, I laid down on my couch and fell asleep and woke up and said, okay, it's time to go home. I then got home Friday night, went to bed, and got up Sunday morning at 8 o'clock. So, needless to say, it was a useful weekend with lots of rest, much needed. But as a result, I said, okay, we need to do something a little different on Monday. So let's go right to the problems and make sure you can understand what kind of problems you're going to see from colligative properties. Most of the problems are pretty straightforward and simple. I've really only given you a couple of equations so far, which are that the freezing change in the temperature of freezing of any solution is equal to some constant K times the molality of that solution. Remember, molality is a concentration unit that doesn't depend on temperature. Which is just the number of moles of solute divided by the number of kilograms of solvent. What's more important is, why does it lower the pressure? Or why does it change the boiling point and the freezing point of any mixture? And you've seen this picture a couple of times, so we'll just look at what the book shows us. There's the graph of what a simple one-component phase diagram looks like. A one-component phase diagram being, if I've got pure water or pure CO2 or pure cyclohexane or any other solvent, anytime I put something into it, I'm going to change the phase diagram to the dashed lines that you see. The freezing point will always go down. The boiling point will always go up. Now, one of the things we did not talk about was, why is it that the freezing point goes down? And we talked a little bit about the mechanics of something freezing. In order to get something to freeze, you've got to get intermolecular forces of attraction. In other words, the attractive forces between different parts of the system to be strongly interacting with each other. In order to get something to melt, you have to overcome those intermolecular forces of attraction. And whatever you can do to put energy in to overcome those intermolecular forces of attraction, one way to do it is simply dump something in there. If I dump sand into water, I'm going to overcome the intermolecular forces of attraction between water molecules, because some of the water molecules will be attracted to the sand. And some of the sand will take over those attractive forces, so you've added energy to the system. Ultimately, it lowers it. The other one we didn't talk much about, though, was vapor pressure. What the heck is vapor pressure? The vapor pressure of any liquid is the pressure of the gas that is over that liquid. Something with a high vapor pressure is going to be something that there's a lot of vapor in there and maybe a little bit of liquid. Something with a low vapor pressure is not going to have a lot. In terms of humidity, a high vapor pressure means a high humidity. A low vapor pressure means a low humidity. There's not a lot of water vapor in a low humidity environment. If you are designing a perfume, do you want a vapor pressure that's high or low? What's the point of a perfume? The point of a perfume is that so that body A over here really gets a good whiff of this one here. So if you really want someone to notice you, do you want something with a high vapor pressure because the aroma gets there quicker, or do you want a low vapor pressure? Obviously, you want as high a vapor pressure as you can get, but if it's too high, what happens? It evaporates completely if the vapor pressure is too high. If there's too high a vapor pressure, as soon as it becomes vapor, what keeps the vapor locked into a terrarium? The fact that it's sealed. If you take the lid off it, what happens to the vapor pressure? It distributes itself throughout the entire environment. And so if you're talking about putting perfume onto someone, and it's got a very high vapor pressure, yeah, you're going to smell it. You've all walked by the person who just put cologne on 15 minutes ago and took a double take because all of a sudden it hits you, and then you met them an hour later and, oh, good, it's gone. Thank goodness we got that off us. But you want it to last a long time, so you want it just enough so that it dissipates, but not enough so it's completely gone. Designing perfumes is very much related to this. It's also related to Graham's Law of Effusion, which we covered very briefly last semester. You saw this once before. Last semester at one point, we talked about collecting a sample of a gas by bubbling it through water. So here we've got some zinc metal. We dump a little bit of HCl in there, maybe add some heat, not necessarily. But when you react zinc with HCl, you get zinc ions and hydrogen gas. And obviously that's not a balanced equation, but that's okay. The hydrogen gas then bubbles through this little tube here, through here, and it's collected over on this side. And here we measure the pressure. And the problem when we did these gas law problems said, calculate the number of moles of hydrogen gas produced if the pressure is equal to 386 torr at 30 degrees C. And what we had to realize in that case was the pressure you measure is equal to the pressure of the hydrogen that you produce plus the pressure of water. Remember we said that if you collect a sample of gas over water, there's some partial pressure of water related to the temperature. As you raise the temperature, the partial pressure of water is going to go up. Well, you all know that already. If I raise the temperature of a beaker of water or of a pan of water, eventually you'll get it to boil. At what point does it boil? What is boiling? The definition of boiling is when the vapor pressure is equal to atmospheric pressure. At that point, when you've got equilibrium established between the two, you are now boiling the liquid. How can you get things to boil at different temperatures? By changing the pressure. At the point where it's boiling, you know that the vapor pressure of water. So if you plot vapor pressure of water as a function of temperature, it's a straight line, and it's got a value of 1 atmosphere at 100 degrees C. So the normal boiling point of water is 1 atmosphere. That's when it's vapor pressure. Other than that, it's going to be some number smaller than that. Does solid water have a vapor pressure? Can piles of snow dissipate in the wintertime without melting? Yes. Why? Because even solid water can undergo a phase change. I can't do it there. Can undergo a phase change from solid to vapor without becoming liquid first. Water will do it too. That's how piles of snow in Minnesota will actually disappear even though the temperature doesn't get above, how cold was it when you were there? -11 Fahrenheit? Ooh, it was warm. Aren't you lucky? So even though it's below 0 Fahrenheit, piles of snow will still disappear because the solid is subliming. Now there's a nice simple relationship between vapor pressure and concentration. It's such a simple equation, and yet, what does it tell you? It tells you that the pressure of gas A is equal to concentration of A times the pure pressure of A. So if I've got nothing but pure A, say A is water, then the vapor pressure of the water will be equal to the vapor pressure of water. Well, that's, even I could have figured that out. Yes, Emma.
What is x equal to again?
About to tell you that. Haven't defined it yet. It's bad when I don't even have to see their face to recognize the name, right? All right. So if I make a plot, and the scale this time is going to go from 0 to 1, the pressure of gas A at any point along this curve is just going to be a straight line. Well, what if this is a two-component mixture? There's gas B, whatever B is. If there are only two things in my mixture, and then the scale here, I'll give you a name for A, X in a second, is from 0 to 1 from left to right for A, what's the scale for B? On the same axis. There's only two things in my mixture. On the far right-hand side, I have pure A. What do I have on the far left-hand side? Pure B. So how much B do I have on the far right? None. So the scale is exactly reversed for B as it is for A. It's a curve that looks like that. Where X is just called a mole fraction. It's a very simple quantity. It's the number of moles of A, whatever A is, divided by the total number of moles you've got in your mixture. For a simple two-component mixture, ethanol water is a good example. For a simple two-component mixture like ethanol and water, you can have some amount of A and some amount of water and some amount of ethanol, but then the total amount that's in there will just be the two added together. If I do a plot of from 0 to 1 mole fraction of water on this axis, what's the boiling point of water? 100 degrees. So at 1 atmosphere of pressure at 100 degrees, we'd be up here. That's what the curve looks like. It's a nice straight line. What's the boiling point of ethanol? Anybody know off the top of their head? How much? You just put it into a table? Yesterday, 44 degrees. Or 65. It's something less than 100. I think it's about 65. So the vapor pressure is going to be a little bit lower, actually. So this is the ethanol on this side. This is water over here. If I add these two together, what does the combined curve look like, do you think? Just add all the points together. There's a nice straight line that connects these. How can you use this? Well, if I happen to be doing an experiment and I analyze my mixture at that point, I know what the vapor pressure is. I know what temperature it's boiling at. I can tell you how much ethanol and how much water there is in the mixture. These are for ideal solutions. The reality is when you mix something together like ethanol and water, and you saw me do this in class last week, what happens to the volume of a mixture of ethanol and water once they mix? It contracted. Ethanol and water mix so that the interaction between ethanol and water is stronger than the interaction of just water to itself or just ethanol to itself. What do you think that does to the boiling point? It's going to lower it, actually. And so what happens is you get, and I'm not going to make you do this, don't worry, you get deviations from the ideal behavior. And so something like ethanol and water, when you mix them together, there is an ideal mixture where you cannot get them more separated than they currently are. In the case of ethanol and water on this curve, it looks something like this in reality. When you've got a mixture of ethanol and water, if I now plot temperature of boiling against percent ethanol, there's a minimum temperature here that it boils at. That's the minimum temperature I can get it to boil at. That percentage is 95%. In terms of proof, it's 190 proof. Proof is just twice the percentage. What is 190 proof ethanol? You can actually go buy it. Everclear. Everclear is a mixture of ethanol and water where what you've done is you've boiled off all the water that you possibly can. How does a still work? The way that a still works is you start boiling the liquid. And think about any time you've seen water boiling in an apparatus in an organic chem lab or in a mad scientist lab. You'll see that there's a liquid running up this thing and then they're collecting it down on the other side. What you're doing when you do that is if I start boiling at this temperature, this curve is showing me two phases. This is the ideal line in between them. Below this line you have liquid. Above this line you have vapor. So when I'm boiling at this temperature, my vapor is going to be that rich in whatever I've got. This entire region in here is a mixture of liquid and gas. And so when I boil the liquid, the first thing that starts to happen is it starts to boil. The gas that comes off will be richer in ethanol than the liquid that is still in the container. So then I take this solution here and I boil it and I enrich it a little bit more. And if you keep doing that, and a still does this, it will eventually get to the point where you can no longer get more water out of the solution. The most water you can get from boiling from an ethanol and water mixture is 95% ethanol. Anything beyond that, you have to do something more. So when I brought absolute ethanol in here the other day, that had to be produced differently. When you do your distillations in lab, the same thing happens. You can only purify it so much. All distillations do the same thing. As you boil the liquid, because of the ideal and non-ideal behavior that's going on, the liquid is going to be one concentration, and the gas will be higher in purity of the other thing. And the more distillations you do, the more you can purify the sample. There's a great picture in your book, and I just ran into this last week, that shows you adding antifreeze to your car radiator. I'll tell you the story. Why do you add antifreeze to your car radiator? To keep it from freezing. Obviously, it's called antifreeze. How does it keep it from freezing? It lowers the freezing point. So it does exactly what we've been talking about. It changes the phase diagram to lower the freezing point. All right, somewhere on here, antifreeze, here we go. They told me the boiling point of antifreeze. What was it? Is it a problem? Oh, there it is. Thank you. It's in the example. Ethylene glycol is a common automobile antifreeze. It is water-soluble and fairly non-volatile. It boils at 197 degrees C. Okay, calculate the freezing point. I'm not going to worry about that. It boils at 197 degrees C. So you go into your local mechanic and your mechanic says, oh, your radiator's low. Let me put more antifreeze in. What should you do? Find a new mechanic. What temperature does water boil at? 100 degrees C. What temperature does antifreeze boil at? 197. If your radiator's low, what's it low on? Water. Why are they trying to put antifreeze in? Because they can't justify charging you for water. So when the mechanic came up to me last week and said, your radiator's low, can I put more antifreeze in for you? I looked at him and said, sorry, it's the last time I'll be at this shop. He looked at me incredulous and I said, come to my chemistry class in a week and I'll tell you why. Anytime, the lower boiling one is always going to boil off first. So when your radiator's low, just dump water into it. You've lost water, you haven't lost antifreeze. It never fails. Use the chemistry and we'll explain it. The other picture they had in here that's great, this is one you'll need for your biology class, is that one. Why is this thing just not in focus? Take the autofocus off. Thank you. There we go. What you've got a picture there is red blood cells in isotonic, hypotonic, and hypertonic solutions. Okay? This is also what happens in a semi-permeable membrane. If I've got a blood cell that's filled with electrolytes of one kind or another, this is the reason why drinking Gatorade is not good for you, contrary to what the University of Florida would have you believe. If you've got no, not Yale, University of Florida, although they're making a mint off Gatorade. If you've got your cell, every cell in your body has some level of electrolytes in it, sodium ions, potassium ions. There's got to be some anions in there as well. All right? Now I take that cell, which is a semi-permeable membrane. It allows water to pass through the membrane and selective ions, but in general it allows water to pass and nothing else. Okay, and if I've got a container now that inside of this water, there's water in the beaker, and this has a bag filled with sodium chloride. What's going to happen as I let that sit there? I'm sorry? The bag is indeed semi-permeable. You've got water will go in. Why will water go in? Because there's a low concentration of water inside the bag. If you compare the concentration of water inside the bag to the concentration of water outside the bag, the concentration of water outside the bag, since there's nothing else in there, is 1. The concentration of water inside the bag is something less than 1. How much less? It depends upon how much saline is in there. All a blood cell is the same kind of thing. If you've got a blood cell that is deficient in water, and you drink something like Gatorade, will it rehydrate you or will it dehydrate you? Now you're taking a cell that has very little water in it and lots of electrolytes, and you're surrounding it by a solution that has even more electrolytes. What's it going to do? Dehydrate you even more. Why does Coke make you thirsty? Drinking a Coke will make you thirstier. It's a great, when they invented Coca-Cola, besides the fact that they may have put cocaine in it at one time, nobody's going to admit to that, but they did one thing very, very smart. They put phosphoric acid into Coke. Phosphoric acid absorbs water. So when you drink Coke, you dehydrate your body. And when you dehydrate your body, of course, your body says put more liquid in. And so what do? You drink more Coke, and you dehydrate your body some more. And you will keep doing that. Drinking Gatorade, all it's going to do is dehydrate your body as well. Because you're putting this excess electrolyte solution in. You've already got a high concentration of electrolytes because you're already dehydrated. And so it's going to draw even more water out. What's the best thing you can do? Drink water. You rehydrate yourself by putting more water in there. At some point, you level them out. This picture shows you what happens if you've got excess water molecules or solute molecules. You can either get your blood cells to expand and burst in a hypotonic solution, or compress and completely shrivel up in a hypertonic solution. Hyper being too much ions in it, hypo being too few.
What's the deal with Gatorade then if all the athletes are drinking it?
What's the deal with Gatorade if all the athletes are drinking it? Well, they may water it down. There used to be a Gatorade gum you could get. Now this is, I remember it well because there was a big 5-gallon bucket of it on the desk of my coach's desk. This is back in 1975. When you sweat, do you sweat out a lot of your electrolytes? Okay, let's think about that for a second. When you sweat, what's happening? Your body is cooling, you're allowing your body to cool off. How does your body cool off? The process of converting water from liquid to vapor, is it exothermic or endothermic? Endothermic. It requires energy. You have to put energy in. Exothermic or endothermic? You have to put energy in to convert from liquid to vapor. Well, if you do that, where's the energy coming from? You, and so it's cooling you off to boil off the water when you sweat. Are you also sweating off electrolytes? No. What are they doing? You've all seen stained shirts after you've worked out. What is the stain on the shirt? The salt. Where did the salt come from? Yes, it carried through your body. Did it evaporate off, though? No, the water did. There is a little bit of it that gets carried through. Do you have to replenish that? No, your body does a great job replenishing it. Your body is a phenomenal system to put all that stuff back. So what's with all these athletes drinking Gatorade? Why does Tiger Woods shoot Nike golf clubs? You pay me $100 million a year, I'll shoot Nike golf clubs too. Gatorade wants celebrity endorsements, just like Nike does, because then you and I, who want to be like Tiger, will go out and buy Nike golf clubs, or drink Gatorade, or Pepsi. The celebrity endorsements, all of us fall prey to the marketers. I kicked myself 8 years ago because I bought a new car. I bought a Honda Pilot. It's a great car, not 8 years ago, 2003. It was when they first came out. Now, at the time, I was the director of marketing for an organization. And then I read this nice article that said the Honda Pilot is marketed to 40-year-old white males with 3 kids. And I said, damn it, how'd they know me? Marketing is a science, whether those of us in the physical sciences want to admit it or not, where they prey upon human nature. We're all prone to it. Why do we want these phones that have, how many of us have flip phones because it's cool to have it? Got to have a camera because everybody knows every once in a while you need to take a worthless picture. This is somebody's phone that got left here. How many of us just need a phone so that we can be busy texting our friends while they're in the middle of chemistry class? Thank you, Jessica. We don't really need a phone. Do we want a phone? Yes. Do we need it? No. So the marketers will fall prey to that.
Actually, the flip phones typically take up less volume.
The flip phones take up less volume. You know, I used to think that too, but there's some great Nokias that are real small that I wish I had that instead. All right, let me try a different problem here for you. I wanted you to see that you should all be not putting any more antifreeze into your cars.
Unless it really overheats.
All right. Problem number 82. I haven't talked about osmotic pressure at all. Osmosis is just the process of going from a high concentration to a low concentration. Osmotic pressure, like boiling point and freezing point, simply depend upon concentrations, the amount that's in there. So there's a nice simple equation to calculate osmotic pressure. It looks just like the ideal gas law. It says the osmotic pressure pi, or P, is equal to mRT. Whoops. Pi is the osmotic pressure. It's equal to the molecular mass times RT. It's an ideal gas law problem even though we're talking about liquids. The reason why this one works, remember last semester I said very adamantly, never, ever, ever use the ideal gas law when you're talking about liquids. The reason why osmotic pressure works and looks just like the ideal gas law is because you're talking about the vapor pressure, really. And so if you want to calculate the molecular weight of something, you can measure its osmotic pressure. So solutions A and B containing the same solute have osmotic pressures of 2.4 and 4.6 atmospheres at a certain temperature. What is the osmotic pressure of a solution prepared by mixing equal volumes of A and B at the same temperature? M in that case was molar mass. Molarity would be bold-faced and underlined usually. So pi equals mRT is molecular mass. Are you saying you don't think so? Amelia wants me to check that. I won't doubt you. I've been wrong once or twice a day before. Oh, Amelia's got me again. Well, M is molarity. Sorry. Pi equals molarity times RT. Thank you, Amelia. She just took the MCAT. I shouldn't doubt her. This one, actually, you don't even need that. Use common sense. If I've got two different solutions, I'm sorry? It's a linear relationship. So if you want, you could do the whole thing, but so pi equals and so the problem says, what is the osmotic pressure of a solution prepared by mixing equal volumes of A and B at the same temperature? Well, we know that the osmotic pressure was 2.4. And the other one said that 4.6. So I've got two different pressures. I've got two different concentrations. If I take the ratio of these two, which is the easiest thing to do, I get rid of R and T. And so M2 equals 4.6 over 2.4 times M1. Now what do I do with it? How am I going to get the concentration or the pressure of the equal amounts of them? Why would I just average them? I'm sorry? If osmotic pressure is proportional to molarity, and now I mix equal amounts of them, the molarities are the same, yes, you just average the two. So the answer is just an average of these two numbers. You have no calculations to do in this one. The answer is just, what, 3.5, 7 divided by 2. I've always liked problem number 83. I've asked it on many years' exams. A cucumber placed into a brine solution, a very saline, heavy solution, shrivels into a pickle. Why? Water rushes out of the cucumber and into the saline, trying to dilute the saline solution. So the water from the pickle leaves, or from the cucumber leaves to try and dilute the saline. And why does it taste salty then? Salt doesn't go in. There's naturally already salt in the pickle, in the cucumber. And so all you're doing is amplifying it by decreasing the water concentration inside of it. Is that how you salt meat? It's exactly the same idea, except what do they do many times when they salt meat? They skip the brine. They just take the meat and put it into dry salt, and then it really will try to dehydrate the meat. It will try to lose as much of the water as it possibly can. Same process.
Really in the pickle?
I'm sorry?
Salt is really in the pickle.
Salt's already in there. Yep. Yeah. Yes. No, we don't have to assume they're the same, but as soon as you mix them, they're the same. And so it's just an average of the two. All right, the question here, number 85, talks about a Van Hoff factor. I've already told you what the Van Hoff factor is, but I haven't had you calculate it yet. Hello? Hey, where am I? I'm at the front of Schmitt Hall. Where are you? No, I don't know whose cell phone it is. I was trying to figure it out. They left it in Schmitt Hall. Let's see, what time is it? Yeah, we'll be here for about another 8 minutes. Tell them to come to Dr. Kenney's office. Yeah, room 205. Thanks. That's whose phone it was. There, we got that solved. All right. The Van Hoff factor. I heard that. In the book, you'll find that the delta TF or delta TB equation has an italicized I in front of it. Remember when we were talking about what should you spread on ice in the wintertime? Sodium chloride, calcium chloride, or urea? Sodium chloride will give you twice the change in freezing than will silicon dioxide. And calcium chloride will give you 3 times the change. The reason is because silicon dioxide, when it dissolves, just gives you 1 particle. Sodium chloride, when it dissolves, gives you 2 particles. Calcium chloride, when it dissolves, gives you 3 particles, a calcium ion and 2 chloride ions. That Van Hoff factor, I, is the number of particles you get when it dissolves. So problem number 85 says, calculate the Van Hoff factor of sodium phosphate in a 0.4 molar aqueous solution whose boiling point is 100.78 degrees C. You think it's 2? Well, if you look at this and you say, okay, sodium phosphate, sodium is a group 1 ion. So if it's a group 1 ion, therefore it is soluble or insoluble? Soluble. So if it's soluble, sodium phosphate, when I put it into water, will give me 4 particles. Okay? So if we think that the Van Hoff factor is 4, then we would say, okay, the change in temperature of boiling would be equal to 4 times Kb. I need Kb for water. Anybody know what the Kb for water is? No, I'd have to give it to you. I think it's 1.86. No, that's Kf. Kb is Come on, you give me delta TF. Where's KB? There it is. KB for water is 0.52. And what was the concentration? 0.4 molal. So let's see, 4 times 0.52 is about 2.08 times 0.4 is 0.8 something. And what did they say? 0.78. It's not quite 4. What if you solve this backwards? Instead of guessing I based upon the ionic equation, let's just solve for I. So delta TB equals so I would be equal to well, what's the change in temperature? 0.78 degrees. It normally boils at 100 degrees C. Again, it's always going to go up, so I don't worry if it's positive or negative. KB, we said, was, I can't remember that long ago, 0.52. Units are kind of strange, degrees C per molal unit, and the concentration was 0.4. Now that one I can't do in my head. I'll need someone with a calculator to do that one. It's going to come out to be 3 point something. And so if you do that problem, why don't you get 4 for an answer? If I take and I say that all group 1 ions are soluble, but this is telling me I didn't get 4 ions. I got somewhere more than 3, but not quite 4. 3.75? Not all of them will dissociate. Why not? Did I lie to you last semester? Probably? Who said probably? It's a two-sided arrow. Oh, you're setting us up nicely. It's an equilibrium. One of the things that we assumed last semester was that every chemical reaction started with reactants and ended with products, and there was nothing in between. The theme you're going to hear from now on this semester is you're going to start with reactants and you're going to make products, but if you start with products, you could make reactants. And so there's going to be a balance set up between moving from left to right and moving from right to left. Sodium phosphate is indeed soluble. It will dissociate into its ions. And it does so nearly 100%. But as this just showed us, it's not exactly 100%. And we're going to spend the entire rest of this semester trying to figure out how to make sense of that. I will see you on Wednesday.